Welcome all to the winter session of C Conversations. I am Dushyant Ashar and I teach at the School of Environment and Architecture. C Conversations are the school's engagement with the world that brings in discursive rigor as well as joys of connecting to new imaginations, voices, and ideas. This is the 18th cycle of C City Conversations, and this series is partly supported by Urban Center Mumbai. UCM is a node for dialogue and ideation to carry out research in sustainable urban development. This winter series of C Conversations titled States of Matter has 6 talks from around the world. This series of talks are curated from the research interests of myself and my colleague Milind in questions of materials, matter, the making of built forms, and new phenomenologies of inhabitation. And this series intends to open up discussions on and interrogations on the dialectical relationship between forest and the factory, the kitchen and laboratory, between technology and phenomena, and between form and matter. So today we are at the second conversation titled Design to Reassemble on the Permanence of Architectural Matter by Oliver Tessmann. Welcome, Oliver.
Hi.
Hi. I'll introduce you and then we will have a presentation of your works followed by discussions and questions from the audience. Oliver is an architect and professor at the Technical University of Darmstadt, where he's heading the Digital Design Unit, the DDU. His teaching and research revolves around computational design, digital manufacturing, and robotics in architecture. He has been teaching since 2008 as guest professor at the Stadelschule architecture class, and from 2012 as an assistant professor at the School of Architecture at the Royal Institute of Technology in Stockholm, and worked at engineering office Bollinger Grohmann from 2008 to 11 in Frankfurt. He's also received his doctoral degree from University of Kassel in 2008. And his works have been published and exhibited in Europe, Asia, and the US. So welcome, Oliver.
Thank you.
We'll start with your presentation.
Thank you very much. And thank you for this warm welcome and introduction. I'm really honored and pleased to be here today and to be part of that really interesting lecture series. And yeah, I brought a couple of slides and I would immediately start sharing and talk you through what I think we need to do to design to reassemble.
All right.
Let me share my screen. You should see my screen now.
Yeah.
Yeah. Okay. Perfect. Good. Yeah. Design to reassemble on the permanence of architectural matter. Before we go deeply into that topic, I would like to show you a movie of an installation that we recently finished, and you will understand very quickly after that why we did what you will see here. And there should be sound. In October 2020, the Center for Architecture and Design in Stockholm had an exhibition that was titled Flying Panels, How Concrete Panels Changed the World. The exhibition depicts the narrative of a techno-optimistic post-World War II era in which a flying concrete panel in the Soviet Union was a symbol for a better future. Prefab concrete was supposed to solve the housing crisis after the war and raise the living standards of millions of people. So a flying concrete panel was next to a rocket that was shot in space, the one thing that kind of stands for a positive future. And yes, the plan kind of worked out in a sense of using prefab concrete to build and to create housing and apartments for millions of people, and not only in the Soviet Union, but the system, and we all know that, spread over the entire planet. Here we see images from Sweden, where in the 1960s, in a program called the Million Program, 1 million apartments were built within 1 decade, which was only possible through prefabricated concrete panels that are flying. Well, they hang on cranes, but they almost look like flying. The cranes are somewhere in the background. You basically see the panels flying to be placed in space and in construction. Well, the panels landed, and I think we are all aware that the quality and the optimistic view of what prefab concrete could do did not always fulfill its promises. We, I think, are all aware of what serial repetition and monotonous suburban architecture made to the cities and to the built environment. However, prefab concrete can, of course, be used to create amazing spaces. And what you see here are images from the building that I'm currently in. It's the TU Darmstadt School of Architecture, which is a hybrid made from on-site, in situ, and prefab concrete. And the spaces from that 1968 building are really excellent as an architecture school, and I used a lot. What's interesting is that in 2019, this building by Farr, Frohn and Rojas architects, a housing, an apartment building in Berlin, finished in 2019, won a couple of prizes for innovative and low-cost housing. And if we look at the prefab concrete details, and if we compare them to the building I'm sitting in, which had been built almost 60 years earlier, it looks like there's zero innovation in prefab concrete. The way we built prefab did not change in the last 60 years. This is a kind of scary observation against the background of the challenges we are currently facing globally, in the sense of climate change, in the sense of scarce resources. So what had been a vision in post-war Soviet Union is the everyday of the construction site. This is what happens. So we have a lot of flying panels, and we all are aware of the fact that flying is quite CO2 intensive, right? So we think we should not fly so much any longer. And also our concrete panels should maybe not fly so much. But in the future, we were wondering whether we could make them walk, we could make them wobble around, we could make them dance. And you just saw the video of dancers interacting with these elements. And the idea, which I will explain a little bit more in detail later, is that if we think of elements that are not only used in one single building, but elements that can be assembled, disassembled, and reassembled in a new configuration, we actually might find answers to questions of CO2 emissions, questions of waste reduction in architecture. But we also might find completely new ways of configuring space, of reconfiguring space, and of humans interacting with these elements to form space and to change space. We have to solve that problem. And the fact that concrete is a problem, I think is very present, not only in our discipline, but it becomes more and more a common sense. The Guardian wrote in 2019 that concrete, the most destructive material on Earth. It's probably a little bit too easy, because concrete is also responsible, as we have previously seen, for providing housing for millions and billions of people. So it's not only destruction, but it also creates our cities, of course. However, common anecdote is that if the cement producing industry would be a country, it would be on place 3 after, I think, China and the US in terms of CO2 emissions. So it's no question that we have to address this problem. So do we now build everything out of timber? Might be a problem. If you listen to Karen Scrivener from the EPFL in Lausanne, and she said, if we wanted to replace just 1/4 of concrete with timber, we would have to plant new forests 1.5 times of the size of India. So you guys don't want to live in a forest, I assume, not completely. And forests need time to grow. So timber is part of the answer, but it could never be a replacement for all of the things we currently use concrete for. So we have to find other ways to solve that problem. And the first thing to look at is the question whether we really want to keep on doing something like that. Yeah, buildings being demolished and blasted, the elements with all their materials, with all their engineering know-how, design ambitions and resources are destroyed or downcycled. It's not because their structure or construction does not perform any longer, but rather because they are mostly economically obsolete. This is the AFE Tower University building in Frankfurt that was demolished due to energetic problems, fire security regulations that changed, but not because of the structure being non-performing, say. So there's of course, a kind of beauty of that movie that was beautifully shot by a team called Woodland Film, who were so kind to allow us to show their movie. There's a beauty in the movie, but there's also a kind of craziness in destroying what is all there, especially if you look at this slide. On the left-hand side, you see the tower being built in the 1970s. In 2014, it was blasted to make space for a new high-rise, which, well, doesn't look so different to what has been there before. So we need to ask ourselves whether this is the way get rid of obsolete buildings and the way we build new buildings. At the digital design unit that I'm heading here in Darmstadt, we are interested in, as we just heard, computational design, in digital fabrication, in robotics, and we think these things belong together. And since a couple of years, we really redirected our forces to address these problems, these challenges that you have just seen. And I will briefly talk about three research projects we are currently working on: scan, print, assemble, precast concrete components, and tactile robotic assembly. And all of them try to somehow relate to the question, how can we work with existing material? How can we build something new within an existing context? But also, how can we design something that can be disassembled and reassembled somewhere else? So in architecture, permanence is usually regarded as the permanence of a building. And I think our discipline as architects, we tend to design buildings that are made to stand there forever, or maybe for 100 years at least. What we see in a lot of cities where the ground becomes more and more expensive is that buildings are torn down after 20 years already, after 30 years. So there's no permanence in the building. And what we would like to look further into is the question whether there could be a level of permanence not in the building, but in the building component that is assembled to be part of a building for 20, 30 years. Then the whole thing is disassembled, and the part in itself is durable enough to be reused in a future building. And that happens again and again and again in cycles. So it's a different notion of permanence and durability in architecture. And that, we believe, also leads to the need for new design and fabrication procedures. And this is what we would like to address. So scan, print, assemble is a project and a research directory, and you can see here kind of a demonstrator of that concept. It is this idea that we have existing elements, in this case random stones that we found somewhere, which are connected in a new way through the use of 3D printed, let's call them adapter pieces, that negotiate between two randomly formed stones. And to make that happen, you first have to 3D scan the stones. You have to 3D the existing context. And based on these information, you can design something new that perfectly adapts to that context. And then you can use digital fabrication, which is made to create unique elements, to create custom-made elements. And if we use this capability of digital fabrication to perfectly adapt to an existing context, then we can bring these two worlds together to ideally form something new. In this case, the researchers tried to form an arc made from random stones and the 3D printed adapters. So we have matter as it comes out of the 3D printer, matter as printed, but we also have matter as we need it in our environment. And to deal with this matter as mat and find new ways of using it, additive manufacturing and 3D printing could be a contribution. To do that, and maybe also to find ways to reduce the amount of new material you have to add in between the existing parts, our team works on algorithmic procedures to categorize these kind of random elements, broken elements. We try to assign geometric features and recognize these features, and then have ways that find ways and methodologies that allow us to reconfigure and reassemble them in novel ways. This is the work of students that combined broken parts again with 3D printed elements, and it's an ongoing research in which we develop new algorithms, in which we use different kinds of 3D printers. Here you can see stones in combination with ceramic prints. The orange adapters were plastic prints. And we look for the challenges that we are facing in terms of the computational design procedures, but also in terms of tolerances, of material properties of 3D printed elements. We are also interested in using and reusing existing building elements. So instead of blasting a building and crunch it down into recycled concrete aggregates, here our student Katarina Koska developed a kind of narrative which she called the concrete hospital. And I really love this project where she says, well, whenever a building is meant to be torn down, we come and we harvest the elements. And yeah, well, they all might have a couple of problems. So they need to go to they need to see the doctor. They need to go through a kind of anamnesis where we look, maybe we only need to polish a little bit. We might need to do a little bit of plastic surgery to make it look good again. We may sometimes need to amputate, so we cut off a piece. And sometimes we might even think, okay, there's nothing to do, so this goes onto the graveyard or being recycled and be broken down into aggregates. Once the pieces get out of the concrete hospital, they might not immediately be reused in constructions. They might wait for their reuse, and while they are waiting, they are being aggregated as a kind of as a bus stop in a city. And so there is a structure which is, let's say, a material and building element storage, and at the same time it's a bus stop that provides shelter for people waiting for the bus. And every once in a while you see the bus coming here, and the bus in the front picks up people to bring them from A to B. But then in the back, also the old precast concrete columns go on a bus tour and might be brought to new construction sites to be then reused. So this is how we like to work in teaching, and how we like to work with our students to come up with ideas, maybe slightly crazy, but we can say that they actually are often starting points for research projects that we are then work on. And this is exactly the case here in the concrete hospital. And what came out of that hospital was a project called Precast Concrete Components 2.0. And we kind of reduced the narrative slightly. We said, well, if there is an old and existing obsolete concrete, steel reinforced concrete skeleton, which is meant to be broken down, we come and scan it and develop a kind of decomposition plan. So it's like construction, but the other way around. And that will provide us with elements. They will be scanned so that we make them digital. And in the digital, they run through the entire geometric feature recognition process. But we can also look at surface qualities. We can look at the reinforcement. And then in the digital, we develop plans of how we need to treat them. They need to be cut. They need new connection details to then become a new precast concrete component, precast concrete component 2.0. German is a little bit more handy title, Fertigteil 2.0. So this is the diagram that we handed in to a funding agency together with Faro, a company that works on 3D scanning, together with a Frankfurt-based startup company that actually works on the logistics, digital logistics of building use. They are meant to moderate and negotiate this entire process chain. And together with our lovely colleagues from Braunschweig, Harald Kloft and his team, who's working with robots on sawing concrete. So what you need to start with, it's quite loud. What you need to start with, of course, is you have to 3D scan the existing context. And again, you might recognize that we are in the Darmstadt Faculty of Architecture building that we 3D scanned with our students. And then we took that point cloud and used it to make this movie. And the idea here is that within such a point cloud, we would identify the beams, but also the columns that could become the members of a future building. And if you are able to do these scans as a building owner, you might have a lot of information whether your building is worth to be used as a building or as a material storage for a future building. Together with Faro, our scanning expert, we then kind of redid this process with a hand scanning device that you can see here on the right-hand side to then turn something like this industrial building into a point cloud, and then out of that point cloud identify certain vertical and horizontal areas that could then be readjusted in the digital model into architectural elements for future reuse. Our colleagues in Braunschweig look then at ways of how to cut such a building into pieces, which kind of pieces can be harvested and what, and then we work again on algorithms that are recombining these structures into, or these elements into new structures. So if you want to assemble, reassemble, and disassemble, you have to make sure that you don't glue any element to another element, that you don't use any mortar. But what you need is having dry joint connections. You connect elements by interlocking them, and then this interlocking is reversible, so you can put that into single pieces again. And this is what we look at in this process. And then on one hand, we develop the new details on the right-hand side, how these things could come together. And on the other side, we use computation and the power of computers, not as we have seen that maybe in the last 15 years of digital fabrication, to make unique elements in this case, but we rather use the computational power to calculate how elements could be aggregated and what are the different ways of aggregating the same elements together. So what you see here are 40 elements that are aggregated in hundreds and thousands of different ways. This is something you could, of course, manually test, but it's much faster if you let the computer run through the different versions of aggregating. So to make that happen, to harvest elements, we actually found something that was really not needed any longer at the TU Darmstadt campus. It's this bridge, and it was meant to be torn down, and we said, hey, we would like to harvest a couple of elements. So it was broken down, and then the two columns were left. And, again, very noisy. We found a guy who likes sawing concrete, and he supported us here in harvesting these concrete elements. And you can see on the left-hand side, they cut and suddenly the column is dancing. It becomes a flying panel, so to say. There's a crane pulling, and we harvest a couple of these old pieces, and these pieces were then shipped to Braunschweig, to our partner Harald Kloft, who, as you can see here on the middle image, puts big sawing blades to robots, which allows him to very precisely cut elements, and he can then create cuts that allow for new details for dry joint connections. If you reuse an element, it's good to record the history of such an element. So we RFID tag it and then collect all the information of where that element was standing. Was it inside, outside? Was it exposed to any hazardous chemicals, or can it be reused in different configurations? So there is something that could be called a passport, a material passport that tells something about the element. New details for dry joint connection. And then in that research project, we of course look at the life cycle of such an element, and we explore whether it really makes sense to reuse these concrete components, and we compare these reuse scenarios, which of course include transport and storing and cutting. We compare all these aspects to fabricating new elements, and we are in the process of doing that. What I can say is it makes sense to reuse, even if there's a bit more work in cutting and transporting. So this project is really about bringing old stuff in, bringing old stuff into the new context. But of course, we should also, as architects, think about how can we design new elements, new modular systems in a way that they can be reused. And again, this is a project which is called Tactile Robotic Assembly. Here we explore how we can reversibly join and interlock elements so that they can be reused in different configurations. And since that is a tedious process to assemble and disassemble, we thought it would be nice to delegate that task to robots so that they autonomously put structures together, but they could also then disassemble them and put them into new configurations. The whole research is based on one single modular element, which consists out of 8 cubes, as you can see on the left. 4 of them form an S shape, 4 of them form an L shape, and then together they are called SL block, which we did not invent, but it was developed by a Taiwanese researcher called Shi in the, I think around 2016, he published his first papers. What's interesting about these SL blocks is that they can be combined, and if you combine them, they interlock. And they can be interlocked in many different ways. Oops, sorry. And these different ways how elements come together are called engagements. That's that's a term that she coined in this context. And different engagements lead to different shapes. You can have linear shapes, you can have diagonal shapes, you can have spiraling shapes, you can have very monolithic and block-like shapes. And so with one single module, you can create a multitude of different shapes. And this is, we think, a very interesting approach where you can put these SL blocks together to become beams, to become columns. Yeah, so we could kind of simplify them and see them as single elements. Yeah? Hundreds of SL blocks form one single beam, and then one single beam could be assembled into a structure. So you create a kind of hierarchy of small blocks forming larger elements that are then aggregated into architectural constructions. This is what we are exploring currently. We look at the algorithms that either top-down take a large volume and break it down into SL block engagements, or we do it bottom-up, that we start with a single module that we aggregate to form different larger global forms. We do that digitally in the computer, but it's also fun to do that physically, to put elements together, elements that are made from different materials, because it's the geometry and the topology of how they interlock that is the, let's say, common denominator for the elements, so that various materials could be combined to form new structures. This was a master thesis modeled by Yuji Liu, who then, after doing the master thesis, immediately started becoming a researcher at the DDU and continues to work on these SL block configurations. We furthermore teamed up with the roboticists at the TU Darmstadt. As I said in the beginning, we work with robots ourselves. So this is a robot from the DDU. It needs a human providing elements, as you can see. And it's actually a very stupid robot. Yeah. We pre-programmed every single step. We told the robot where to pick up an element. And you can see that the human agent in this movie is even providing the SL blocks in different orientations. And then the robot comes, knows where to pick it up, and knows where to travel and to build, and to put that together. So it's all designed and developed in a digital model and then sent and delegated to the robot. It's a stupid and blind robot that's just executing commands. Now, teaming up with computer scientists and roboticists from TU Darmstadt allowed us to test other ways to assemble and also to test other hardware to do that. What you can see here is a dual-armed robot called Franca Panda. And that robot is equipped with torque sensors in all of his joints. So that robot is aware of collisions that might happen. And if he tries to assemble elements and he's not perfectly finding the right spot. He might be a few millimeters off. Then what he can do is to make his joints soft, so that there's a certain flexibility in this moment of assembling elements. So what we did here is we 3D printed those as L blocks, and you can see that they have rounded off edges, which allows them to slide into each other. So assembly is a little bit easier because there's a moment of almost self-calibration where two blocks meet, they slide into each other, and the robot is soft enough to support that process. The other approach that we had been working on with our roboticists is to use artificial intelligence. In this case, it was a machine learning approach where the robot tries to put these elements together, and whenever there is a certain friction, he stops and he tries to approach this assembly moment from a different direction. And the whole measurement and the sensing of frictions and problems during the assembly is done by this gripper. You see the lights in that gripper. It's a system which is called tactile sensing, which allows the robot to understand whether there are collisions, whether there's too much friction to put things together. And then you can see that he tries to put the element together in different ways. And it's interesting how to get there. And there's another example that nicely explains that. Here you can see a roboticist researcher showing a robot to play table tennis. Of course, the joints of the robots are loose, so he can move freely. And what he's done here is he records the movements that he does, guided by the human. He records the accelerations of the joints, the movements, the positions. So he has a kind of principal idea of how table tennis works. And then he's asked to do it himself. And you have to imagine that room being equipped with a camera system that can see whether a ball hits the table or is off. And whenever the ball hits the table, the robot gets a reward. And whenever it is off, it gets punished. And by that, the system starts to learn to play table tennis. And when we saw that movie, we thought, hey guys, this is the perfect technology that we could use to assemble blocks. So very similar approaches were used in the previous video of putting SL blocks together. Again, with the conceptual idea of assembling, disassembling, and reassembling, with the idea of maybe see these SL blocks not as scaled down models, but maybe in the future we put a lot of small elements together to form construction elements like the beams. And the permanence and durability of matter is not in the beam itself, but it would be in the SL block that travels from one construction site and one building to the next one. And in case they are a little bit bigger, then it would be nice to allow for interaction between elements and humans, and to not make them too heavy. It's good to have hollow elements. It also saves a lot of concrete material. And the technology we use here is called rotoforming. And what you see here is actually a balloon that we pre-stressed as a membrane. And then we pour in concrete, and then we rotate that element, and what happens is that the concrete evenly distributes at this membrane surface, and what you generate is a hollow object which is lightweight. You wouldn't be able to carry a massive concrete block with your arm like this. It's hollow, it's sequentially casted, so we can vary the thickness of the element wall, the wall thickness. And again, we work with students on developing new kinds of formwork systems where we tension the membrane, where we are in control, geometric control of how this element is tensioned. We developed new machines for rotor molding, and in this case, it was used to build a kind of node system for space frame structure. We explored with our students various ways of how that could be used, and I very quickly go through that because I run out of time. So it could be columns, producing columns, building machines. Get your hands dirty in our studio to do something like this. Sometimes they break and you only have the digital representation as a mesh. Sometimes it works out. Could be a flooring or ceiling panel. It could be a beam. It could be modules. So this is something that we explored in a design studio with our students, and we try to develop a kind of phylogenesis to identify where are the most promising locations for using this technology for building elements. We scaled the process. We scaled it up together with an industry partner and a larger robot to build these kind of column systems. And again, what you see here are hollow elements that form a column. Now, if an element is hollow, it might have its center of mass in a location where you would not expect it to be. And what I mean by this can be shown in the Animate Concrete project. This is not us, this is David Henry, an artist, and there's quite a bit of wobbling going on, and we clearly see that putting the center of mass of that thing very low allows you to do crazy things with a piece of concrete. And this is something we were interested in transforming into an architectural context. Yeah. Think of dry joint elements that could be rotated, but then combined and interlocked to together form something new. And I'll rush a little bit through these images. So interlocking structures that roll, that have their own kind of behavior, that are almost characters, that move on a plane, that dance like a choreography. And it again requires new ways of designing them. How do they interlock when they move? Our team developed a couple of extremely beautiful, I think, drawings of how these things come together, physical models to test that. Sometimes goes wrong. Here you can see on the left-hand side that the center of mass is, of course, put to the very left of the object by making it massive at that point. You don't see that from the outside, and you are then sometimes surprised by the weird behavior of the elements in motion. And to understand that a little bit better, we motion captured them, pushed them to move, and explored the different movement pattern. I rushed through that. You can see some results from the studio and the design, or the aim in this case was to design elements that could be composed in different ways. You can put them together in one way, and then disassemble them and reassemble them in other ways. And we then luckily got invited for an exhibition called Robots That Build in the Netherlands, and we used this invitation to develop a larger installation, which you have seen in the beginning of that movie. So students designed these pieces that were then realized through roto forming them, and there might be, yes, there are some images that you can see here. So mixing material, having the formwork linked to the robot, put in the liquid material, and then use the robot to distribute the material along the formwork system, leading to elements that are hollow, that are lightweight, and that allow people to interact with them, to rearrange them, and to rearrange space. And I think that's the end of my talk. Thank you very much. And I stop sharing at this point.
Thank you, Oliver. It was a very good presentation. I mean, there are so many thoughts and ideas that have kind of triggered in this presentation, and also the kind of rigor by which I think all of these tests and research has been carried out. I mean, I just would want to kind of look through a few ideas that kind of caught some interest, and also there have been some parallelities between what you have shown and partly what even I am engaged in my own school, in our own research project. So especially the rotoform and the rotocolumn idea, we sort of kind of converge there. We are working with gravity-based apparatuses, which really, where we don't really need a robot. We don't have the means to really have the robot with the school right now. So we looked at gravity, which forms material within its influence. So I think maybe we will open a few of those up, but I would like to kind of also speak of the ideas that came up. The building as a raw material actually was quite a strong point to sort of start, and we have been discussing these ideas over here. And I think what that brings up is a new landscape of materials, or new landscape of matter that really opens up for not just the construction industry, but I think for many other kinds of industries and disciplines, because like nature really does that. And I think that our understanding, or maybe our capabilities of knowing and kind of gathering information from an existing element to really reuse it has allowed this possibility. And thinking of materials to be harvested is something that can only come with probably having a scientific know-how of what is and what can be done. So that's one sort of area which was quite interesting. And also I think the references that you made in the start of the ground or the land becoming more expensive than the buildings, where it economically becomes obsolete. But I was just kind of interested to also open up the economics or the possibilities in this process of cutting down a building to really rethink or reassemble a new possibility. So this was one set of thoughts that were going on. Following this, I just want to connect to one more idea which was there over here. Is a new tectonic that really comes in. It kind of shatters or kind of fragments this whole idea of an element or of a building element, and those fragments really kind of compose or reconfigure build form, like the example of the beam, or maybe the example of the the hospital, where the element, when broken up, it kind of becomes, I mean, it was already a type, the typology of that building was then broken down or cut down, and then there was a new typology that sort of emerged from those parts. So here I think the precision, the way we work with precision right now, the industrial logics of how precision works have kind of shifted to a new set of thinking of precision, because the rock or the stone that you found or matter as met is not considered precise. So I think it opens up a lot of these questions for me, as well as I think that the possibilities of new tectonics which emerge from here, and the shift in typological possibilities, or maybe new types emerging from here, are the kind of coordinates that really kind of were very interesting for me. So maybe if you could sort of open up a few of these discussions.
Yeah, you addressed the question of the precision, and I think that's an interesting one, because I mean, I showed a lot of conceptual ideas which we sometimes more, sometimes less try to drag into the reality. So in Germany, often funding is provided to teams of researchers, university with companies, and then it's always the question, can we make that transfer? Which I think is a smart way of doing it, because it doesn't help to develop ideas in an academic context already alone. They need to be transferred into practice, right? And in that sense, it's good to form these teams, even if it's a hard work to work together, to also identify the interests that we really share, and the economic interests of a company that, of course, needs to pay their people, and on the other hand, an academic research interest. So sometimes we start with ideas like a lot of interlocking stuff that, I mean, we met at the Städelschule architecture class many years ago. And even at that point, I was interested in topological interlocking structures. They are based on almost on the idea of zero tolerance, means perfect industrialized serial production, things that fit together, and only if they fit, and you almost want to have a bit of friction when you put them together. This is what makes them form a structure, and this is also what makes them being reusable. We can take them apart and reassemble them. On the other hand, you saw the matter as met approach, which comes more from a digital fabrication approach, where in, let's say, the early 2000s, a lot of architects, including myself, were enthusiastic about the fact that you can do almost anything with digital fabrication. How it started, and that's interesting, and I think that changed in the last years. How it started was there was a kind of ideally a star architect creating a complicated shape, which then a lot of engineers were happy to take as a problem that needs to be solved. How do we break that continuous surface down into elements? How can we build these kind of things? Let's say today we know we can build anything if we throw a lot of resources, materials, and money on the problem. So it's no problem. So finding new ways of using digital fabrication, a way that it makes a contribution to our environmental questions, to also socio-economic questions is something which actually fascinates me. So in Germany, we have a big discussion whether should we train our architecture students to build something new, or should they only engage with the existing context? Of course, it's not black and white, but what I see missing is a level of digital construction in the context. It's not happening, and this is where we think we can suddenly maybe again create precision, where the orange adapter meets the stone, but it's a different notion of precision, and it suddenly appreciates, as you mentioned, it appreciates maybe natural materials, unprocessed materials, or you get something that is reused, that is broken out of another building, which then becomes a new life. It goes to the hospital and gets a prosthesis, so to say. If we want to turn our discipline into circular one, then I'm convinced that there will be, of course, a certain era of transformation where we do this urban mining. We have to take the stuff that was never being designed to be reused. It was meant to be destroyed once it's obsolete. And then we need to refurbish it to become a circular element. Ideally, we overcome that phase at a certain point, and we only build stuff that is made and foreseen to be assembled, disassembled, and reassembled. But that will be, of course, a period of transformation in which we are currently in now. And one thing that hopefully became clear in the presentation is this is not a purely technical problem. If we delegate that to the engineering world, they will solve circular economy. No doubts that this will happen. But maybe what we lose is a certain design quality of our built environment. And that's where I'm really get excited when we collaborate with dancers and choreographers who then take these elements and interact with them, because suddenly you see them on a different level. And they also tell you, look, these objects, they had been so fragile, we were always afraid of destroying them. Could they be a little bit more robust so we can really dance with them, we can really interact with them? Well, there are these new requests and new questions to us, how we can think these things further. And ideally, we have an engineering paradigm that allows for reconfiguration, but we as architects suddenly gain new freedom of designing houses that the users can fundamentally rearrange. If they don't like the space, they flip, rearrange it, deconstruct it. Or you have a robot in your office and every morning you enter the office, it looks different because overnight you rearranged it. Yeah. That might be crazy, that might be poetic, but I think we need that level so that it's not only a technical question.
Yeah, and it's, I think, very important that you bring this up, because I was constantly thinking when you presented this idea that why not say retrofit a building, and I was constantly thinking that there is a question of aesthetics and form, which really pushes one to kind of pull it apart and kind of remake it. And I think that's where for me, I think that's where the economic question was. And I think that to invest into not just say saving money or saving materials, but at the same time with the spirit of looking at new phenomenological or possibilities, or maybe the formal possibilities that these elements reconfigure with. And I think it affords many different kinds of spatial or as you, and I want to link it back to the first thing that you mentioned, that there's no innovation in a prefab building ever. And I think this has been that, that is a quite interesting response to that premise. But in the same context, on the other hand, I was interested that when these elements come together through this process, what is the base for the algorithm? Like, what does the algorithm really consider? Is it the technological, or maybe you can say, is it the structural parameter by which it kind of puts things together, or there are say other associational, elemental, and typological parameters that the algorithm operates with?
Mm-hmm. Yeah, we of course work with different algorithms. One, I think, very interesting first approach was a software, an open source software called WASP. It became a plugin for Grasshopper, and it is a design tool that allows you to aggregate discrete elements. And what the software does is it takes an element and you define where you allow this element to be assembled with another one. Like two blocks of Lego can be put together in various ways, but always in a 90-degree angle. Yeah, there's a certain constraint of how it is assembled that is embedded in the geometry of the element, which is interesting. You don't need to have a plan to understand how blocks are put together. You figure that out once you have the elements in your hand. It's a little bit similar to the SL blocks. So WASP allows you to represent that digitally. This is the block, and this is how it is meant to be assembled with other blocks. And it could be not only one way, but several ways of putting that together. And then you can use computational power to bottom up aggregate discrete elements. And you can do that along reference geometries. You can also define certain void areas where you don't want elements to be put. You could foresee certain structural capabilities and constraints in those aggregations. So it's a new design tool and a new method to work with discrete elements. If we look at this meta-as-mat approach, it's slightly different. It is about, well, you get random geometry into your system. It's not a module. It was never meant to be put together. It is maybe even a fragment of what has been a module before. So what you need to do is you have to define certain features to describe it. And those features need to be numerical features, so they can be represented as vectors. And the more feature vectors you have for such an element, the more precise you can describe it. And the more precise you can maybe compare two elements with each other, or combine different elements with each other. And that's interesting because I think we are currently all excited about ChatGPT, this amazing AI-driven chatbot. And if you look at natural language processing, then it works in a way that, well, you let a machine read the entire internet ideally, and then every word is represented as a vector with, I don't know, 1,000 dimensions. And these dimensions define relationships to other words. Yeah? So in which context, text context, do certain words appear? And with this categorization, the AI develops an understanding of understanding of language. Yeah? It creates correlations. It kind of positions a word in certain context. And it's a little bit similar with what we are currently doing. We take an element and we try to look at the geometric features, and they are not necessarily it's a cone or a cylinder or a sphere, but we kind of fragmentally analyze it. And the more features, again, we have, the better we can contextualize it and put it into a new context. And this is work that we use computation for. If you look into architectural history, then it's a concept that exists since probably 4,000 years, and it's called spolia, right? People always took stones from old buildings, from ruins, to build their new buildings, because it was expensive to work with stones, because there was a lack of tools, for example. And so it was good to take something that you find that almost fits what you were looking for. And that became the concept of spolia. Sometimes it was also a demonstration of power, right? If somebody conquered the castle of somebody else or the church, it would take the stones of the most prestigious element and make that the foundation of its new building, just to show I can do it. I have the power to do that. But it's interesting that we don't come up with a completely new concept. We kind of jump from today and computation and the age of the digital. We jump over the 20th century industrialization, serialization, back into an era that is more craft-based, and suddenly we find a lot of connections, which could help also to provide a certain cultural dimension to circular economy as well, because there's a history.
Yeah, actually, it's interesting that you bring this reference of cultural associations, because we find that even here, where the temples the temples and the mosques had this kind of thing, where when the Mughals came to India, they tore down a few temples, and the elements of the temples were actually used to make mosques. And in that process, what happened is that the typology of the mosque from Persia kept changing as they moved. And in India, a lot of motifs from the temple became the type that is associated now with a few mosques. So in that sense, I think it's quite an interesting typological sort of and also socio-cultural sort of shift that this process brings into. But at the same time, I think that what this process, the digital trouble that from the scan to print to assemble, I think that project was quite interesting for me, because the way it moved from the physicality of a quite random stone, a form, to a very precise digital information of that stone. And it kind of returns back to the matter as printed, where and that's the kind of tectonic that I was trying to kind of bring in. And I feel that it really goes beyond our current elemental associations of architecture, or maybe our association of precision, or our associations with say a complete block or a geometrical sense that we have right now with say beams running along, or maybe columns in a vertical perpendicular position. So and I think in that sense it shifts this whole, not by complicating it with the question of surface, as you were mentioning, or maybe complex geometries per se, but I think it kind of harvests not just material, but harvests geometries and forms And that's where I think this question of precision, like, because in our research here, I am kind of questioning this precision as a means of making architectural form. And I think your study brings in other interesting perspective that, to kind of relook at precision in other ways to kind of generate new forms beyond, this highly, you can say, intense use of softwares like Rhino or other NURBS-based modeling software. So I think that it's not just matter that is met, but also geometry or form that kind of meets. So I think that kind of opens up quite interesting possibilities here for. And on the other hand, the production or the relationship that we have with material coming to a site and going back, I think here is where the material from the site itself. I can think of this as a lab, which say one person could easily kind of mobilize with the scale of elements that one deals with, or maybe even an apparatus where these rotoforms or like one robotic hand could possibly be enough for one person to really. So in terms of construction, in terms of really the labor which goes into making all of these, is also kind of interesting for me in terms of how we link it not just through the kind of scale of things, but also the economic, not to reduce or not to kind of say it's cheap, but in terms of being more efficient or being more relevant in that sense to one person or one scale or one group or one set of. So I think in that sense, it kind of shifts this agency of making or shifts the agency of building, and the reliance on current structures of say how buildings are mobilized, how construction is mobilized, kind of shifts quite a lot. And it's not just the rudimentary, I would say now I would call it rudimentary 3D printer that is next to your desktop or a laptop, but it kind of becomes an apparatus where it allows these kind of possibilities.
Mm-hmm. Yeah. I really think that to make that shift, we need to break 2000 years of architectural thinking. Yeah, from a European perspective, we look at Vitruvius, the ancient architectural theorist, one of the very few written sources about ancient architecture. And this is where the idea of permanence, let's say, starts in written form. So since that time, through Renaissance, for us, permanence is seen in a building. And this is not something that you change within a decade or two. What is interesting is that we currently see also legislation changing. We see politics being aware of the need to change. And on a European level, a lot of companies need to change the way they work currently through something like the new EU taxation, where suddenly, as a big company, you not only provide your finance report to the public, but also the supply chain, where is stuff produced, and under which condition it is produced. What is the climate impact of the material you're using? And that becomes the second thing next to the financial reporting of how you perform. and it is meant to be it's a political instrument that is meant to force, of course, companies to develop new business models. So architecture, we often like to see ourselves in a bubble, having a discourse with our colleagues on aesthetics, on construction. But of course, we are part of a larger socio-economic and political system. And we will see now that that's my hope. There are new constraints and new pressures, political pressures, that force companies, hopefully also construction companies, to rethink the way they act. And then, again, it's good that we come with ideas and are not passively waiting for them to activate their engineers to solve problems only on a technical level.
Yeah. I second that, and I'm aware of the European restrictions, or maybe the rules that are so stringent and are so tightly packed. I think I really agree with all the things that you said, and I think that also makes us open for questions from the audience. I would read out 2 questions that are there from anonymous attendees. So the question, I think both of them sort of are quite related. So while using the building elements of existing buildings into a new building, how do we determine the strength of the elements, since the loads are different for different buildings? And the other is, what is the scope of using waste debris as a walling material? So
so thank you for those super relevant questions. And especially if we think of reusing steel reinforced concrete, it is a question of what's happening inside such a construction element. We cannot really look into it. We of course have the means of X-ray it or make a computer tomography. We could do that in research for 1 or 2 of them, but you cannot do that for millions of them being reused. So what that means is that we need to change the way they perform structurally. So we know that concrete is good in taking compression forces, and since it's not so good in taking the tension forces, we put in steel reinforcement. Now, if we have such an old piece, we don't know about the condition of the steel. What we do is we try to reuse it in a way that it is only exposed to compression forces. So imagine that you put elements together and then they are all tied together with a post-tensioning cable, so that this new cable is tensioned, and with that tension it generates compression on the existing elements. And if you manage to have constructions like this, then the old steel reinforcement does not play a role in terms of the performance, the structural performance of the building. So this is one way to react to this unknown. In our precast concrete component project, we also said that we will harvest only elements after the 1970s, because after 1971 there was a new building code in Germany, and if you take elements from earliest that era, you have a general idea of the performance of such an element. We have a lot of post-World War II constructions that went up super quickly, and from the 1950s, and you don't really know about their performance. So we say we don't use them, but we rather go for the younger elements. So let's say you have an idea of the amount of steel that's in it. We can, of course, see the reinforcement on the faces of the elements where we cut. We might use the capacities of artificial intelligence for image recognition. That's what AI is currently extremely strong due to the autonomous driving. There's a lot of power in image recognition, and a question could be, can we benefit from that to categorize? Well, if we have certain features on the surface of an element, we should rather not use it, or use it in a compression only way. But it's still an open question which is not solved yet. No. And what is the scope of using waste debris as a walling material? If I understand that question correctly, then it is, what kind of waste can we use to build a wall? And it addresses maybe a little bit the question that I briefly presented in my talk about a material passport. So if you buy a new product, it's usually certified. It complies to certain national rules of that define what quality standards need to be fulfilled. If you take a broken down piece, then you don't know maybe where it comes from, how it was used, how old it is. But these information might become relevant. And how do you store them? They should travel with the piece. Every piece should have a passport to talk about its history. And if you reuse concrete from a chemical plant, you might not want to reuse that in the kindergarten. Yeah. So the quality, we need to find ways to ensure the quality of building materials. We need to be able to identify hazardous materials before reusing. But of course, we have the same. With new materials. We can see first houses being 3D printed currently, and the concrete that is used for 3D printing is, of course, not the one that you use on a general construction site. It's full of chemicals made to control the rheology of the concrete, controls the time frame of hardening. And there are a lot of researchers asking the question of shouldn't we monitor what comes out of these materials once they build a house where you live in? So it will become a new research area, I think. Maybe not so much for architects, but for material scientists to find out what is it that we can reuse and what is it that we should maybe not reuse. So a lot of work to do still.
Yeah, definitely, yes. Any other colleagues who have some questions or comments? Okay, Joel, can we have Anuj?
Yes, sure.
Yeah.
Hi.
Thank you so much for your wonderful talk. And while you were explaining, I thought
it fits so well within even our concept note of matter between the laboratory and the kitchen, because actually you were giving us a method of cutting and chopping buildings, and that also reminded me of Meta Clark. I mean, Gordon Meta Clark was literally kind of cutting buildings into halves to open up space, and you were also kind of using that method in order to reconfigure or reassemble space. So I thought that was a particularly interesting moment. And what I was thinking constantly is that if we cut buildings in the way that these building elements are now, would we not end up reproducing the spatiality as it is today? And so, and therefore, when you showed your last slides where there was this dancing man on the hemisphere, I was thinking of how our forms of occupying space are also changing with increasing virtuality. For example, Beatrice Colomina debates about how our much of our lives are spent in our bedrooms today, and she talks about the 24/7 bed. And so I was also thinking that if we kind of interpose these two things about not reproducing the same kind of spatiality and being able to speculate a new kind of program or a form of occupying, then how would we chop buildings today? So yeah, I mean, this was just a thought, and if you would like to respond, it will be really nice.
Yeah, thank you very much. We, of course, came across Gordon Meta Clark and his work and used it also for references. We once did a design studio in which we reused one of the old World War II bunkers that we still have in cities with like 2-meter thick concrete walls. And they've never been torn down. They are also hard to reuse. So we speculated on cutting them and then introducing a very lightweight rotoformed structure, so that the heavy concrete suddenly talks to the lightweight concrete and how that could come together. So there's a fascination on this end about Gordon Meta Clark's work as well. So we have that in common. I think, and I tried to say that earlier, the need for reversibility, for reversible connections opens up a completely new field of architectural design. And we again speculated on that together with our dancers in a way that we said, let's build something that at least reminds of the scale of structural elements. It's almost a column that you can suddenly rotate. And since its center of mass sits in such a weird spot, you only need to tip it a little bit. And once it reaches this tipping point, it rearranged in a new stable position. So this is not a structure yet, but this is, let's say, maybe a suggestion for others to do further research on whether something that acts for 5 years as a beam is then rotating into becoming a column.
Yeah.
And suddenly your building changes. And I mean, it's yeah, can we, I said that earlier, we have this debate, do we build at all new structures or should we reuse existing things forever? I think, again, it's not black and white, but having this moment in between of being able to change the space beyond the wallpaper and some plaster boards that you rearrange. Can we go as deep as into a structural element suddenly becomes something new, is for me a kind of fascinating idea. Yeah? To have this contrast between something you expect to be heavy and load-bearing and non-mobile, immobile, suddenly becomes a thing that changes and provides something new, and also allows me to interact with it. Yeah. So it's not the panel that flies in and I wait for it to come. It's the one that I'm interacting in my everyday environment with.
Yeah, that's very interesting. And while you were saying that, I was thinking about how, there's this huge recycling market for building parts, which are salvaged from dilapidated buildings in India. I'm not sure if that happens in Europe too, but there are these large kind of markets where doors, windows, frames, and grills, all these things are salvaged from dilapidated structures, and they are kind of stored and auctioned for new buildings. And these are mostly kind of taken further rather by people who build their own homes, informal houses, and so on. So it's very kind of, it talks to the process that you are trying to set up in your laboratory in that sense. And I can imagine then, there being a market also for these salvaged columns and beams and concrete parts and so on. So yeah, it would be very interesting to see in the future.
It's super interesting because I would say in Germany we do not have an informal construction going on. Everything is like super formalized. Yeah. So I'm pretty sure that in India there's a lot more experimentation going on.
Yeah.
What we did a couple of months ago was to use Midjourney, this AI image generating thing, to let it design buildings from reused parts.
Yeah.
And well, since these AI exploit global human creativity, doubles it. It was interesting to see that there were very little ideas of how such a building could look like, which means that it's not part of our global thinking.
Yeah,
it's really new, and that was a fascinating finding, that even the AI is kind of clueless about how that could look like.
Yeah, yeah.
A lot to explore there.
Yes, absolutely. Yes, great. Thank you. Thank you.
Thank you.
Thank you. So if there are no further questions, we would if there are no further questions, we would call it a day. But if anybody else, if they have a question, please let us know. But in the meantime, Oliver, it was a very good conversation. I really enjoyed this works that were kind of discussed and presented, and I think we draw a lot of parallelities and commonalities in the process that we do here. It's not as digitized as as your process is, but we kind of are very close. We are very computational, but not very digital per se. So in that sense, I think yeah.
I think it's the thinking that has to be computational, not the equipment. I mean, a lot of concepts that we use today have been invented in the 1940s and 50s without any hardware.
Yeah.
It was the mind of people. So in that sense, that's not the decisive moment.
Correct. I think there are no more questions, and we would conclude the session. And thanks a lot for accepting, for coming, for sharing. I really enjoyed it, and I think we look forward to be in touch and look for sharing more ideas.
Great. Thank you for having me. Okay.
Thank you. All right.
See Goodbye.
You. Goodbye.